are advancing to the right. Also for convenience, I want to point out that there is a kind of someone drew with a red pen, drew a spot onto the medium. That's like the piece of the carpet pattern. Okay? Notice that that is not moving to the right. That is simply oscillating up and down in place. Okay? So the wave moves this way, but the actual point on the medium just oscillates up and down. I guess one of the classic examples of this is when you get the wave at a sporting event, right? So everyone kind of sequentially goes like this. And you might say, that's not a real wave. That's perfectly a real wave. It's a traveling disturbance that is moving around the sporting event, right? There's no human beings moving with that, okay? All the individual people are just moving up and down, right? That's exactly what the points in the medium are doing. By the way, I should mention that this blue arrow, that blue arrow is the velocity of that point on the medium. Notice that's not constant. It slows down to 0 at the crest and troughs because that's where it turns around, and it goes the fastest through the equilibrium. Now, anytime you see a profile like that, you should think, well, what kind of motion? What kind of motion is that red dot undergoing? Simple harmonic. It's going to be simple harmonic motion. Well, I guess it's harmonic motion technically, but it actually ends up being simple harmonic motion. So the points in the medium do not have constant velocity. So we sometimes differentiate between, I guess I'll turn the lights on for a second, between v, which is the wave speed, in other words, the speed of the disturbance, that is constant based on the medium. That is not to be confused with Vy, which is what we call the transverse velocity of the medium itself. That, in fact, is classic simple harmonic motion profile. So you might wonder, how is it possible that you can have all these particles of the medium moving up and down in this transverse velocity that has this classical simple harmonic motion profile? The velocity of those particles is not constant. How is it that the medium itself can have a disturbance that is traveling at a constant speed? Let me show you. So what I'll do is I'll add a point. I'll add a point to the medium. I'll draw a second red dot. That'll be a second red spot on the carpet pattern, okay? And I want to point out that both of these undergo exactly identical simple harmonic motion. It's just one is slightly time delayed from the other. That is what can give the wave its constant speed from left to right. This idea that even if any individual spot does not travel at a constant velocity, the offset it has with the next point is constant. So, and again, going back to the sporting event, right? If you go back to a sporting event, when it's your turn to do the wave, I assure you, you do not get up at constant velocity. Most people have trouble getting up at first, and then they kind of jump up at the end, right? Your velocity up out of your chair is not constant, right? That's like the transverse velocity here. It's not constant. But everyone has pretty much the same reaction time, which means that if you see that the wave is coming up, it's about to be your turn, everyone reacts about the same speed. And then the next person reacts a little bit later than you, and the next a little later than you. That is how you can have that none of the particles in the medium themselves are at constant velocity, and yet the whole disturbance moves at constant velocity. Okay? So there are two velocities here, and one of them is constant, the other is not. The other thing I do want to show you on this applet, you notice here on the bottom, there's a setting which says f times lambda equals constant. So that's, of course, our representation of v equals f lambda. So if we constrain the frequency times the wavelength to be constant, that's a realistic situation where the wave speed is fixed. So what that does is it allows me to increase the frequency, but you notice the wavelength slider will vary inversely, right? Okay, so what I can do is get a sense of the wave speed. So let me, I guess, try to count this. 1, 2, 3. It's about 3 seconds across the screen, so that gives me a sense of the wave speed. Now, let me go to a very high wavelength, low frequency wave, like this. Because the crests are further apart, you see them less often. So now the crests are riding crest, crest, right? We have a high wavelength, low frequency wave, and yet the wave speed hasn't changed. If I count how long it takes for a crest to go across the screen, I get 1, 2, 3. So this wave is still moving at the same speed. It's just because the crests are further apart, I see them less often. High wavelength, low frequency. Are there any questions on that? Okay, so there's some wave basics. The one order of business we have left, I guess just because the projector is hard to turn on and off, I'll move over here. The one order of business that I have remaining is to tell you how you compute the speed of a wave. Let me tell you how to compute the speed of a wave on a string. You have to know about the string. Here's the equation. And I'll tell you what all these terms mean, of course. F is an old friend. It is the tension in the string. We've used capital T as tension for pretty much the entire course. We don't want to do that now because T is being used for periods, so we use the next best thing, F. F is for force, because tension is a force, right? So this is the tension in the string. It's measured in newtons. And the other quantity in the denominator is the fancy word for this. It's the linear mass density of the string. It's another way to put it, which is slightly less fancy sounding. It's the mass per length in the string. It's literally, if you took the mass of the string and divided by its length, you would get this quantity. It's measured in kilograms per meter. So it's not quite density, right? Density is kilograms per cubic meter. It's linear density because it's just how much mass is carried along the length of it, okay? So those are the two things that we need to know about a string in order to know this wave speed. What is the tension in that string, and how much mass does that string carry per length? If you want, you can even think of linear mass density sort of like just the thickness of the string. Okay? Of course, how thick it is just assuming you're making out of a constant material, right? You can have a string that carries more mass per length without being any thicker if you just make it out of something that's denser, right? So since I just pulled this out of thin air, I do want to do a few relationships with it so you kind of get an intuitive sense of how this works. Where this equation comes from is applying good old F net equals ma to a string, right? So Newton's second law can be applied to lots of things, including a string. It's a lot of work, a lot of crazy math that you have to do, but that's what you end up with. Let me give you a little flavor of it. So here we have a string, and we have a crest of a wave. Remember, the wave is moving like this. So let's take a look at that chunk of string that's at the crest. Well, we can go back over here to our animation and know that once you're at a crest, the only place to go is down, right? By definition, the crest is the extreme. You better come back now. So if the equilibrium of the wave is here, you're going to have to accelerate toward that, right? That's the classic simple harmonic motion profile, right? That you always get pulled back toward the equilibrium. So how does that chunk of string get that acceleration? Well, that chunk of string is not alone in the universe. It's got the string around it pulling on it. So it's got a tension. And as we learned, tension always pulls, never pushes. And it pulls along the rope. Seems weird here because we're applying the idea to one chunk of string as surrounded by its neighbors. So at that point, when you have a crest, the pieces of string around it pull in those directions. If I were to do the vector combo of those two, like there, what would be the overall net force? Straight down, right? The horizontal parts would cancel. Remember that the piece of medium is not moving one way or the other, it's just moving up and down. So the horizontal parts cancel. So if you have something like this, we're trying to add these two. The horizontal parts cancel and the vertical components add. And so we have that the force will be in this direction. And that's good because that's the direction of the acceleration. So what we then have is that if you pull the string tighter, if the string is tighter, it has more tension in it. Well, then that's how much more harshly that piece of string is going to get pulled back down, right? If you increase this force, it increases the acceleration. It's going to yank that thing back down really hard. Well, if the crest goes to equilibrium really fast, it means the crest had to move out of the way really fast. So you can see in this equation, if you tighten up the string, then the wave moves along faster. It has to, because any given part of the medium gets pulled around that much harsher. Okay? So that's one thing to take away from this. If you tighten the string, you'll make the wave travel faster on the string. It literally increases the restoring force that acts on any given piece of the medium to pull it back toward equilibrium. So if we just apply good old F net equals ma to this, we've simply said that if you have a larger F net, you will have a larger acceleration. Well, of course, the other bit to this is what about the mass or inertia carried by that bit of string? We also saw, this is of course a classic result, that for a given amount of net force, if the mass is larger, then the acceleration will be smaller. So what that means, of course, is that if you have a very tight string, but the amount of mass carried here is very large, then the acceleration won't be as violent, right? A given force can't cause as much acceleration. And we see that also, the shadows of that in our equation here too. If more mass is carried per unit length, then it causes the wave to slow down. Okay? So if you tighten this string, you increase the restoring force, it'll make the wave move past faster. But if you put a lot more inertia along the string, it literally carries more mass per unit length, then it'll slow down the speed of the wave. Okay? So really, these two terms are just shadows of F net equals ma. So it's what happens if you increase the force and what happens if you increase the mass, right? How does those affect how the string behaves? Okay. And I'm making a big fuss about this, not only just because this is a useful formula in and of itself, but all wave speed formulas come in some variety of this. So all wave speed formulas that we'll look at, so when we're trying to figure out the speed of the wave on the medium, they all have some variant of, there's something going on with the restoring force or something like that, or restoring agent, I guess more generically. And then there's always some kind of inertial term on the bottom. They all take that form, okay? So when we get to the speed of sound in air, we can rely on the fact that that structure is basically the same. We'll have something in the top which represents how harshly does the medium snap back, and something on the bottom which will say how sluggish is that part of the medium to snapping back. Okay, are there any questions so far? Yeah.
Previously, you told us the wave of the speed is always constant.
Correct.
It's not constant for these.
Well, so remember, it depends on the medium. So usually the tension in a string and the mass density of a string are constant. So that means this will be constant. So what I was saying is that it's constant based on the medium. So these properties don't normally change for, like, if a wave travels along the string string has a uniform tension and the string has a uniform mass density, right? So this is what sets the wave speed, and then it'll be constant from there, right? Does that make sense? So that is how that constant value is determined, right? Does that sort of make sense? So we normally don't have strings. If we have a string that's lying like this, the tension is the same all the way through the journey, and the mass density is the same through the journey. So that will mean when the wave travels along that, it'll travel at a constant speed. This is just what sets that constant speed in the first place. Any other questions? Okay, so next order of business, let's go ahead and take all these ideas and take it over to a sound wave. So here's a sound wave. I guess I can make it a little bigger. So this would be the analogous sound wave to what we've been talking about, a wave on a string. So what we have is a tube of some kind. And so the tube basically sets the axis that the wave can travel on. And what we're doing over here is we are alternately compressing and expanding the air. So we're creating that longitudinal disturbance. We're causing a disturbance that is along the same axis as the direction of travel. Okay? So if you stare at this for a while, it's, you know, if you kind of zoom out, you can clearly see the crests there. The crests being these regions of bunched up air, right? Those are regions of high pressure and high density. Okay? And halfway between them are the troughs where you will find relatively low pressure, low density air. Because of course, if you're going to create periodic compressions, you got to pull the thing back. And when you pull the thing back, you create regions of lower pressure, right? So you can clearly see that there's a disturbance moving along here, a regular periodic disturbance. But if you zoom in on a particular air molecule, it does not travel with the wave. If you look at any particular particle, it's just oscillating in place. Now, it's easy to imagine for a carpet or a string, right? If you have a pattern on a carpet, obviously the pattern doesn't shake out. It doesn't take matter with it. If you draw a dot on a string, when the wave comes by, it doesn't take the ink with it. But it's harder with a sound wave because we like to think of a sound travels through air, and air can flow, right? The pattern in your carpet can't swirl around, but air can easily flow. And yet, let me point out that you can hear me, but you can't smell the pizza with onion that I just ate 5 minutes before I came to class. There are no actual molecules coming from my mouth to your ear. It's a disturbance that's traveling. There is no actual physical stuff coming with it. Okay? So again, we can talk about all the same stuff, very similar. In fact, let me just draw this compression disturbance. If I were to draw a schematic representation where my air at equilibrium was at PATM, right? That's the equilibrium that I start at. And I could draw a representation of the high and low pressures that I have around that. Well, I just have to loosen my idea of what amplitude really means. It doesn't actually have to be physically amplitude. So instead of calling it A, I might call it pressure amplitude, which I usually write PA. So it has a certain amount of pressure above and below atmospheric pressure. And I guess this is a good time to point out that really it's kind of like giving the gauge pressure. Right? Remember that gauge pressure was specifically designed to tell you how much above or below atmospheric pressure you were, right? So if we instead baseline this to 0 gauge pressure, and then here we have positive gauge pressure, and here we'd have negative gauge pressure. All the pressures are positive, of course, but gauge pressure can be negative. That simply means you're below atmospheric. So that's one way you can describe the amplitude of a sound wave. It's literally in terms of pressure variation around atmospheric. The other thing I should point out is that you can literally talk about the physical motion, right? They have a physical displacement back and forth that looks like this. They all have an equilibrium location, and these air molecules are just oscillating around that. This I'll call S max. That's called the displacement variation, or displacement amplitude. So there's actually two different languages for describing the displacement of a sound wave. In terms of physical displacement, so this is called the displacement amplitude. That's measured in units of meters. And this is called the pressure amplitude. And that's measured in pascals. Those are two perfectly fine descriptions. They're complementary descriptions of the amplitude of a sound wave. Okay? So, all I need you to know is that they are complementary to each other. You can use one description or the other. And the other thing that I guess I should point out is that they actually don't co-occur. So when you have the air particle at its maximum displacement, it's not maximum pressure. So these do not co-occur. Do not co-occur. I guess I'll say a few very brief words on why that makes sense. So first comes the pressure wave. The pressure wave sweeps through. Pressure is like force per area, so that's what applies the force. Force applies acceleration. But it takes time. Once you have an acceleration, it takes time to move. So then comes the displacement. And by the time you've had a maximum displacement, the pressure has already moved on. So first comes the pressure variation, then comes the displacement variation. First comes love, then comes marriage. First comes the pressure, then comes the motion that comes with it. Okay? So pressure causes the motion to initiate, and by the time that you have moved S to S max, the pressure is already moved on. Okay? There's only one thing I need you to know that for, and that's when we get to something called standing waves on Thursday, where it'll be helpful to know that those are the two complementary pictures of wave amplitude and that they don't happen at the same time. Okay? So that's pretty much it. Everything else is good to go. We've got a wavelength. We've got frequency and period we can talk about. We have the wave speed is the only order of business because obviously this does not make sense. We can't talk about the tension in the air. I don't know that's a saying, but it's not literal, okay? So we need a new formula where how fast does the sound travel through air, and we are going to refer to this idea that speed of a wave is determined by the medium itself, in this case, the air. So let's knock that out, and then we'll move forward. here is the equation. I'm not going to expect you to do much with it. This is more for your personal thing because this is one thing that may have application to you in the future. This is the speed of a sound wave. And it does have that classic pattern where in the numerator there's some sort of restoring agent, and in the denominator there's some inertial term. The denominator, that's back to our old friend, not some weird linear density, it is just the density of the material. Okay, so this is the density of the material. So that's back to good old, how many kilograms does it carry per meter cubed? The thing in the numerator, I've used B for buoyant force. That's not what this is. This is something completely different. This is called the bulk modulus of the material. Okay? So this is the bulk modulus of the material.